Hi, so for this problem, it says that the woman works for 30 years before retiring. At the end of the first year of employment, she deposited 5,000 into an account for retirement. At the end of each subsequent year of employment, she deposited 3 more than the prior year. The woman made a total of 30 deposits. She will then withdraw 50,000 at the beginning of the first year of the retirement and will make withdrawals at the beginning of each subsequent year for a total of 30 withdrawals. Each of these significant withdrawals will be 3% more than the prior year. The final withdrawals depletes the account. The account earns a constant annual effective interest rate. Calculate the account balance after the final deposit and before the first withdrawal. Okay, well, we got to notice that this problem consists of two different parts, right? So for the first part, it says a woman worked for 30 years before retiring, and at the end of the first year of employment, she deposited 5,000 into account for her retirement. So this would be the first 5,000, right? And we are depositing 1 and 2. We notice that the account earns a constant annual effective interest rate, right? So if we see this 5,000, we notice that this is going on towards the end of 30 years of her working, right? So we notice that this first 5,000 would accumulate to 1 plus I to the 29 up until time 30. Why? Because this 5,000 is occurring at the end of the first year. So if we were to try to discount 5,000 by moving it 1 up 2 years, 3 years, 4 years, we will see that there will only be 29 effective interest rates for 5,000 to accumulate to the time 30. If it were to occur at time 0, then it would be 1 plus I to the 30, but it's occurring here, so it's 1 plus I to the 29. So that's 1. 2, it says that she deposited 3% more than the prior year. So that would mean that into year 2, it would be 5,000 times the effective rate of 3%, since it's more than the previous, times 1 plus I to the 28, right? Now, the sequence is going to go on up until time 30, when at time 30, it's going to be the base of 5,000 times growth rate of 1.03 to the 29, since it's always less than the time, the exponent is always 1 less than the time that it's occurring at, times 1 plus I to the 0, right? Now, we want to find the accumulation amount of this whole sequence. So what we're going to do is we are going to set up an equation, right? Well, we know that 5,000 is a common factor in all of these. That's 1. 2, we could set the first term as a common factor, and we could set up a new geometric progression. So I'll show you what I mean. So for the first part, the first sequence could be 1.03 over 1 plus I, but to the 0. So all of this will equal 1. Why? Because 5,000 times 1 plus I to the 29th is the first term, right? But if we move on to the second term, we will notice that the second term should be 1.03 over 1 plus I. And this whole fraction should be to the first power. Why? Because then the second term would be 5k times 1.03 times 1 plus I to the 28. So we would multiply this and divide this, so this would go down to 28. So this sequence would be continuing until the last term would become 1.03 over 1 plus I, right, to the 29th power. So this is our geometric series, some of the geometric series that we need to solve. Now, the thing here is that the problem is we want to simplify this as much as possible. So what we're going to do is we are going to use the partial sum of a geometric series. right? And what is that formula exactly? Well, it consists of 1 minus r to the n over 1 minus r. Now, what does that mean? Well, the r is denoted as the ratio that we're dealing with, and n is denoted as the number of terms that we're also dealing with, right? Or the number of years of some sorts, right? So again, we could take this term out and we could simplify this within this equation. So we would do 1 minus the ratio that we're dealing with, which is 1.03 over 1 plus I to the 30th power, because there are 30 terms that we're dealing with in this sequence, over 1 minus the ratio again, which is 1.03 over 1 plus I, right? Now, then we find out that the accumulation formula is gonna equal this 5,000, 1 plus I to the 29th term times this geometric fraction, right? Now we can simplify this geometric fraction even more. So what I'm gonna do now is I'm gonna erase this so I can get more space. Hold on. Just okay. Partial sum of geometric series, remember that. So what I'm gonna do is I'm gonna change this to like a full fraction, right? I'm gonna do 1.03 to the 30 over 1 plus I to the 30. I'm gonna change this to 1 plus I to the 30. Right? Now I'm going to take this. Minus. Okay, so I fully simplified the numerator of this part, right? Now this part is going to be so then this one will become I minus 0.03 over 1 plus I, right? So that is the denominator of the fraction. Now we want to divide these fractions, right? So I'm going to flip this, right? Because that's what we do when we divide. I'm going to flip this. I'm going to multiply it by this huge fraction over here. So I could cross out this. This becomes 29. Another thing here is that it's connected to here. So I could cross out this and I could cross out that. So now, as a whole, I'm going to end up with, let me get my eraser So as a whole, I'm gonna end up with 5,000 times 1 plus I to the 30 minus 1.03 to the 30 over I minus 0.03, right? Now, another thing now is that now we have this part 1 solved, right? Now we need part 2. So for part 2, it says that she's going to withdraw $50,000 at the beginning of the first year. And we'll make annual withdrawals in each subsequent for 30 withdrawals. Each of it will be 3% more. Okay, so now what we're gonna do for this one is, we know that 50,000 beginning of the first year. So 50,000 is being withdrawn in the beginning of the first year in this case. And it says that withdrawals are going to be 3% more than the prior year. So again, this multiplied by the effective rate of 3%. And then another thing here is that we aren't withdrawing payments, right, for retirement, which means that withdrawing is a present value concept. So we're going to discount these payments, right? So it's going to go on until we get our 30th payment at time 29, which will be at 1.03 to the 29th over 1 plus I to the 29th. And of course, this whole thing multiplied by 50K. Now, what we can do is that we already found out that our common ratio is 1.03 over 1 plus I. So what we're going to do is that we're going to take 50,000 out. And we're going to make a sum. So 1 plus the ratio of 1.03 divided by effective 1 plus I, which is denoted V, plus for the next term 1.03 over 1 plus I squared, right? Then 1.03 1 plus I to the 29th, right? So now we can again make the same equation as before. Again, what is the partial sum of a geometric series? It's 1 minus r to the n over 1 minus r. So what we're going to do here now is we're going to keep the 50,000 at the outside. We're going to multiply it by 1 minus the common ratio 1.03 over 1 plus I. How many terms are there? There are 30. Over again 1 minus the common ratio 1.03 over 1 plus I. Now, after we do that, we see here that we're able to calculate the account balance after the final deposits and before the further withdrawal. That area that we need to calculate the balance occurs at a comparison date between these two scenarios, which would mean that we would have to set these two functions equal each other to find the effective interest rate at first hand. And because since they're equal, these equations are equal from the time that the balance accumulates from the time that we withdraw. After we find the interest rate, we could input it to either equation to find the account balance, right? So now we're gonna erase this over here, right? Now what we can do is we can get rid of 3 zeros here, 3 zeros here, 5, 5. So this will become 10. Another thing here is, I can, let me observe something. Okay. Well, another thing is that I can simplify this. So again, for the numerator for this one, I could do 1 over, right, and this one's, right, so then it would be 1 plus I to the 30 minus so this is the numerator, right? Yeah, the denominator is and this would become I. Okay, now I could flip this. It seems like a similar scenario as the first part. So simplify, this would become 29. Yeah. Now, yeah. So this whole thing would become 10 times 1 plus I to the 30 minus over 1 plus I to the 29 times I minus. Now let's see. I noticed some similarities. I noticed that we could get rid of this because they're the same. Also noticed that we could get rid of this and this one. So then we're just left with 1 equals 10 over 1 plus I to the 29. So then I just be 1 plus I to the 29 over 10. Now let's get rid of the 29. 129 So I'm going to take out my calculator. I'm going to do 10 to the 1/29. And it's going to be 1.082, and then I'm going to subtract 1. I'm going to get 0.082636734 as my interest rate, right? Now, I could take this interest rate and input it to in either of these equations to solve, right? So what I could do is I can just input it in the case 1 scenario, right? So I'm gonna take my eraser. And this is choice 2. Right, I'm gonna take my answer of the I that I found, which is 0.08267. Then I'm gonna input it here, so I'll do 5,000. Then 1.08263 to the 30 minus 1.03 to the 30 over 0.003. Now let's solve this. I'm going to do 1.08263 to the 30 minus 1.03 to the 30, which is 8.397084, divided by 0.08263 minus 0.03. Okay, I get 159.549. Then I'm going to multiply that by 5,000. Then I get 797,746.99. So the thing is that I don't find any exact answer that's similar to that, and I feel like it's because I might have not kept all of the decimal places when calculating this. But I know that A is far out, B is definitely far out, and D and E. So I'd say C. And also, yeah, so I think the answer is C. And another thing is that I just feel like with geometric increases and like problems like this, whenever you find like an effective interest rate like this as well, you should just always keep all of the decimal places so you could find a full-on answer. But the answer that I got was maybe just 100 off from this, but it was still in the 797 because I got 797,746.9967. So yeah.